Hello everyone, I'm Professor Xiaonan Gao. Welcome to the General Chemistry class. This session will continue with the atmospheric gases and hydrogen chapter. The focus of this session is the combination of noble gases, oxide of carbons, and hydrogen. Let's start with the noble gases. In 1785, Henry Cavendish found that the air contains an unreactive gases making up no more than 1/120 of the whole. John Rayleigh and William Ramsay isolated this gas 1 century later in 1894 and named it argon. The name of argon is derived from the Greek argos, lazy one, meaning inert. Its inability to form chemical compounds with any of the other elements, called the chemical inertness. Afterwards, Ramsay began a systematic search, and other inert gases, helium, neon, krypton, and xenon, were sequentially found. Air contains only 0.000524% of helium, and 0.00181 neon, and 0.932% of the argon by volume. The proportion of krypton is about 1 ppm, and that of the xenon is only 0.05 ppm. As you can see, their existence in air is very limited, so we usually ignore their influence in chemical reactions and industrial productions. However, noble gases still possess significant commercial values due to their inertness. The efficiency and life of electronic light bulbs are increased when they are filled with argon-nitrogen mixture. Kryptons and xenon are used in lasers and flash lamps in photography. In addition, they can serve as the inert atmosphere for metal welding, and another example is the helium balloons. Since the hydrogen is very easily explosive, so helium, which is light but inert, became the optimal candidate for airships. The second topic is the oxide of carbons. Since you are already aware with carbon monoxide and carbon dioxide, let's start with the combustion of the carbon compound. Carbon dioxide is the only oxide of the carbon formed when carbon or carbon-containing compounds are burned in an excess of air. So excess of air means abundance of oxygen. This condition exists when a fueling mixture is burned in an automobile engine. If the combustion occurs in a limited quantity of air, carbon monoxide is also produced. This condition prevails when the fuel-rich mixture is burned in an automobile engine. One possibility for the incomplete combustion of octane is this: carbon monoxide as an air pollutant comes chiefly from the incomplete combustion of fossil fuels in automobile engines. Carbon monoxide is an inhalation poison because carbon monoxide molecules bond to the iron atoms in the hemoglobin in blood and displace the oxygen molecules that is the hemoglobin normally carries. Moreover, excess carbon dioxide pollution nowadays is the main reason for global warming, since it plays a role of greenhouse gas to prevent the heat releasing from the Earth to the universe. And that is why everyone nowadays is encouraged to live in a low-carbon lifestyle. Although carbon dioxide can be obtained directly from the atmosphere as a byproduct of the liquefaction of air, the industrial method for preparing carbon dioxide is still needed. Let's see some common methods here. First, the recovery from exhausted stack gases in the combustion of carbon sources fuels, such as the combustion of coke, and recovery in ammonia plants from the steam reforming reaction used to produce hydrogen. And third, decomposition of limestone at about 900 degrees Celsius, and fermentation byproduct in the production of ethanol. So these are the production of carbon dioxide. For carbon monoxide, the modern method is a steam reforming of natural gases, represented as this reaction here. When carbon dioxide dissolves in water, it produces a solution generally referred to as carbonic acid. Carbonic acid is a weak acid that ionizes in two steps. When the acid is neutralized in the first step, a salt variously called hydrogen carbonate and acid carbonate or bicarbonate is obtained. If the neutralization is carried through the second step by neutralizing the acid carbonate, then a carbonate is obtained. The reaction just described what can be reversed by adding an acid to a carbonate. The carbonic acid breaks down into carbon dioxide and water, and this is a simple way for preparing carbon dioxide in the lab. The last topic in this session is hydrogen. To prepare hydrogen gases, water gas reaction is usually used as follows. Water vapors encounter carbon at high temperature to produce carbon monoxide and hydrogen, and then carbon monoxide can further react with the water vapor to produce carbon dioxide and hydrogen. Another way is a reforming of the methane. Methane can react with water vapor at high temperature, while carbon dioxide and hydrogen can be produced at the end. There's also a method we know in high school. Active metals. They can react with acids to produce hydrogens. Like zinc reacts with sulfuric acid. It produces hydrogen. Hydrogen forms binary compounds called hydrates. With most of other elements, binary hydrates are usually grouped into three broad categories: covalent, ionic, and metallic. Water, ammonia, and methane are very typical covalent hydrates. Ionic hydrates form between hydrogen and the most active metals, particularly those of group 1 metals and group 2 metals. Ionic hydrates react vigorously with water to produce hydrogen. Like calcium hydrates, a gray solid, it has been used as a portable source of hydrogen for waiting weather observation balloons. Metallic hydrates are commonly formed with the transition metals, and we will discuss about that in the future. Alright everyone, in this session we learned the noble gas, oxide of carbons, and hydrogens. I hope you have enjoyed the class, and I'll see you next time.